Dear students, in the previous lecture, I have discussed about the posets, its definition, Hayes diagrams, etc. Now we will start with the elements of poset. The elements of the poset are as follows. Maximal element. Maximal element. Maximal element is an element A belongs to set A is called a maximal element of set A if there is no element C in A such that A is less than equal to C. Minimal element. Now minimal element, an element B belongs to A is called a minimal element of A if there is no element C in A such that C is less than equal to P. There can be more than one maximal element or minimal element. See one example to understand what is the elements of posets, that is maximal elements and minimal elements. First example, you see, determine all the maximal and minimal elements of the poset whose Hayes diagram is shown in the figure 9. This is figure 9. The maximal elements are B and F. See, this and this are maximum elements. The minimum elements are D and C. Minimal elements are, this is D and C of this. Now see one more example. Let A is equal to 2. To make you understand better about this, better you just see this example. Let A equals to 2, 3, 4, 6, 8, 24, 48. This is one set with partial ordering of divisibility. Determine all the maximal and minimal elements of A. See, maximal element is 48. Why it is 48? You just see this definition. An element A belongs to set A. Suppose I am taking this element 48 which belongs to this set A, is called a maximal element of A if there is no element C in A such that A is less than equal to C. There is no element in this set which is less than or equal to this 48 which I have taken as maximal element, and this is your definition. That means the maximal element is 48. The minimal element are 2 and 3. According to minimal elements definition, an element B belongs to A is called a minimal element of A if there is no element C in A such that C is less than equal to B. See this one, so your example. Minimal element 2 I have taken. So there is no element which is less than this 2. This also, this idea goes with 3 also, because there is no element other than 3 which is less than. Less than is there but not equal to 3. So the minimum element are 2 and 3. So in this way we can find the elements of poset, maximal, minimal elements, and you try to solve more examples in the book it is given, and see how to do. So start with another topic, that is upper bound and lower bound. What is upper bound? Consider set B. Consider B be a subset of partial ordered set A. An element X belongs to A is called an upper bound of B if Y is less than equal to X for every Y belongs to B. See this definition very carefully. Consider B be a subset of a partially ordered set A. A is a subset of B. An element X belongs to A is called an upper bound of B if y is less than equal to x for every y belongs to B. See this lower bound, you should remember this definition, very important. Lower bound, again consider B be a subset of a partially ordered set A. An element Z belongs to A, that is set A, is called a lower bound of B if Z is less than equal to x for every x belongs to B. See this example, you can better understand this definition by this example. See one example. Consider the poset, partially ordered set A, 1, 2, 3, 4, 5, 6. These are the element of poset. Be ordered as shown in the figure 9. This is figure 9. Also let B is equal to 3, 4. In this set, in set B, there are two elements 3 and 4. Determine the upper bound and lower bounds of B. You have to find out the lower bounds of 3 and lower bounds of, upper bound and lower bound both of 3 and 4. Set B, in fact. The upper bound of B is 4, 5, 6. Why? Because every element of set B is less than equal to 4, 5, 6. Because in the set A we have two elements 3, 4 which are less than 4, 5, 6. So the upper bound of B is 4, 5, 6 because every element is this. The lower bound of B is 3 to 1 because 3 to 1 are less than equal to every element of B. Likewise, you can try to understand this example also. Alright, so in this way I have shown you these two definitions. Now come to the another topic, which is isomorphic ordered sets. What is isomorphic ordered sets? Suppose A and B are partially ordered sets, that is posets. A bijection f such that f is a function of B, A is a function of B, is called an isomorphism if for all x, y belongs to A, x is less than equal to y if and only if fx is less than equal to fy. See this one. If there is such a function, we say A and B are isomorphic. See with this one, whenever two posets are ordered isomorphic, then they can be considered to be essentially the same, in the sense that one of the orders can be obtained from the other just by renaming of elements. Further, it can be shown that two ordered sets are isomorphic if and only if they can be drawn with identical diagrams. You try to understand this one. Isomorphic ordered sets once again. Suppose set A and B are partially ordered sets. That means two posets. But yes, you have to remember this. You have to keep in mind that posets. What are posets? What is posets? Like whenever we discuss about set A, you just imagine in your mind that yes, what is set A, or what do you mean by set A. Likewise, you have to, or like that, you have to remember whenever it is said that suppose A and B are posets, that is partially ordered sets. So automatically all the definitions of posets should come in your mind, so that it should be clear, yes, what is going to be said, what is going to be the real picture of this posets. So suppose A and B are partially ordered sets, a bijection function f from A to B is called an isomorphism if for all xy which belongs to A, x is less than y if and only if f of x is less than equal to f of y. If there is such a function, we say set A and B are isomorphic. We can understand this thing by this example. Let A is equal to P of 0 1 ordered by subset. Let B is equal to 1 2 3 4 1 2 3 6 with n is less than equal to m if and only if n is belongs to m, then A and B are isomorphic. Alright, now you just see some more examples, some more theorems to understand this one. Suppose A, B and C are partially ordered sets, then A is isomorphic to itself. This is very important theorem actually. A is isomorphic to itself. If A is isomorphic to B, then B is isomorphic to A. And the third point is, if A is isomorphic to B and B is isomorphic to C, then A is isomorphic to C. See the proof. Let us suppose f is a function from A to B and g is a function from B to C are isomorphisms. Note that g of f in a bijection, and if x y belongs to A, then x is less than equal to y if and only if. Just now I have studied this definition, f of x is less than equal to f of y. Since f is an isomorphism, if and only if g of fx is less than equal to g of fy, since g is an isomorphism. So just try to remember this example and this theorem. One more theorem is here. You can say any partially ordered set is isomorphic to a subset of a power set ordered by the subset relation. Let phi is a function from R to S by phi A is equal to IA. We first show that phi is a bijective. By the definition of S, phi is surjective. To show that it is injective, suppose AB belongs to A and phi A is equal to phi B. Since A is less than equal to A belongs to IA, and which implies phi A is equal to phi B is equal to YB, so A is less than equal to B. Similarly, you can see this one. Similarly, B is less than equal to A, so A equals to B, and phi is injective. These definitions I have already given in the last article. Now given A, B belongs to A, we need to show that A less than equal to B if and only if IA is a subset of IB. Suppose first that A belongs to IB, then A belongs to IA, subset of IB, implies that A is less than equal to B. Conversely, suppose A is less than equal to B, then for any x belongs to IA, x is less than equal to A and A is less than equal to B. So S is less than equal to B, and hence x belongs to IB. This shows that I belongs to IB. Now we will discuss lattices. What is lattices? Before starting the lattices, see a little bit definition from lattices. A lattice L, see, a lattice L is a poset in which every pair of elements has a least upper bound LUB or supremum and a greatest lower bound that is called infimum, GLB, that is infimum. See the definition, which is very important. Lattices, what is the definition? A lattice, which is noted by L, is a poset in which every pair of elements has a least upper bound, or it is called supremum, and a greatest lower bound or infimum. join. Consider a poset L under the ordering this relation. Let AB belongs to lattice L. Then supremum AB or supremum AB is denoted by this. Just see, this is least upper bound, or supremum AB is denoted by this, or A supremum B, and is called the join of A and B. That is, A supremum B is equal to, you can write SUPAB. This means supremum of AB. Now this is in case of supremum we use the word join. Now meet. Consider a poset L under the ordering this. Let AB belongs to L, then greatest lower bound AB or infimum AB is denoted by this A, this one or this one, and is called the meet of A and B. That is A cap B, it is shown here, which is equal to infimum AB. From the above it follows that a lattice L is a mathematical structure with two binary operations, join and meet. It is denoted by L, that is lattice, this is join, this is meet. The lattice L for any elements A and C satisfies the following properties, that is commutative property, associative property, absorption property. Commutative property, that is A join B is equal to B join A meet B is equal to B meet A. Similarly associative, A join B, A meet B meet C is equal to A meet in the bracket B meet C. A join B join C is equal to A join B join C. Absorption property shows A meet A join B is equal to A, very important, and A join A meet B is equal to A. So this is very important definition to remember. Now theorem, prove that if L be a lattice, then A meet B is equal to A if and only if A join B is equal to B. Let us prove it. Prove. Let us first assume that A meet B. A meet, that is what in the last, just see here it is. What does it mean? When this arrow is like this we used to see meet, and up above one in the upper open side it is join. So let us first assume that A meet B is equal to A. Using absorption property we have B is equal to B join B meet A is equal to B join A meet B, which is equal to B join A. This can be written from the property, and B join A can be put as A join B. Conversely, let us assume A join B is equal to B. Assuming again using the absorption property we have A is equal to A meet A join B, and this means what? A join B. From 1 and 2 we have A meet B is equal to A if and only if A join B is equal to B, hence the theorem. So in this way many more theorems we will discuss in the next coming lectures. You can see also this example theorem. This is not in fact example, this is theorem. Consider lattice L, prove that the relation A is less than equal to B defined by either A meet B is equal to A or A join B is equal to B is a partial ordering on lattice A. Try to understand this one. If you will not be able to understand, then we'll discuss in the discussion lecture. So in this way we have completed this lattices definitions portion only. Some examples also we will discuss in the next lecture and many more. Thank you so much.